The third lecture on network science continues with the definition of shortest path. The shortest path is also called as a geodesic distance. So that's just a rephrase. And but the definition of it is quite obvious that it says that it is a path between two nodes such that no shorter path exists. So of course, this is a nice concept of measuring distances between nodes or pair of nodes in the network. And with the distance, I mean, with the shortest path, we can even state, um, definitions like shortest distance, which is the length of the shortest path. Well, if the network is disconnected, so if it has multiple components, then of course it can have no path between some of the nodes, and there is also a nice note here that shortest paths are always self-avoiding. It's obviously true because if we have a graph somehow, and then we measure the shortest path between two nodes, then if we start the path and then all of a sudden we get back to a node which we have visited already, then of course this loop, let's say, or cycle doesn't need to be there. So then of course there could be or there is actually an even shorter path. So it's always self-avoiding, the shortest path. Then the next thing is that it's not necessarily unique. So there could be multiple shortest path between two nodes. And from the shortest path, there is again a definition which is a global measure again. So it assigns one number to the one integer number actually, or natural number to the graph, which is diameter. And the diameter is the length of the longest geodesic path. So the longest, shortest path, basically. And if the network is disconnected, so if it has multiple components, then it could happen that we don't have the shortest path between some of the nodes. So then we can define the diameter as infinite, or maybe it does make sense to define the diameter for the components instead. Okay, now talking about components, that is the case when the network is disconnected. We can call it like that. Now, if we consider the undirected case, then it means that the adjacency matrix is symmetric. Okay, this is just a reminder. Symmetric. Okay, and apparently it also turns out that in this case, I mean, if the network is disconnected, then the adjacency matrix can be written in this so-called block diagonal form. Okay, so imagine that here inside these blocks there are some non-zero entries, but outside of these these blocks all the elements are zeros, all the entries are zeros. So this is an interesting thing to consider, because actually the slide says that the adjacency matrix can be written in this block diagonal form. So it turns out that finding this arrangement is highly non-trivial. Why is it the case? Because it's the matter of matter of labeling the nodes. So 1, 2, 3, and so on, six, whatever, 8, 9, and so on. Okay, so if we have a graph and then we label the nodes in a random fashion, 2, 3, 4, and so on. I don't continue. So if we label the nodes in a random fashion, then it can happen that that apparently we get the blocks really separated. But it can also happen that, well, I mean, maybe this one here, we name it as 5, and hence this edge is not here, for example, or these two edges are not here. So what I mean is that, and still in the, I mean, yeah, okay. So sorry, I messed it up. So we can still have the labeling in such a way. Okay, let me just put it back. So I on this graph I can't make a good example. Sorry about that, but you understand. I hope that the this block diagonal form depends only and exclusively on the order of how we label the nodes here. Okay, and if we label it in an unfortunate way, then maybe this block diagonal form doesn't appear, although the graph itself is yeah, unconnected, disconnected. Okay, so that's one thing. The other thing is that how can we, so if there is an algorithm to find the components in the graph, and the answer is yes. If we run a breadth first search on the graph, then sooner or later, so breadth first search needs to visit each and every node, and then if it stops before visiting every node, then we know that it's disconnected. So that's an efficient way to check connectedness. Okay, so we will see hopefully later in some computational tools such as iGraph in R, in the programming language R, that, and also in Python, NetworkX. So all these libraries, graph or network science libraries, they have functions such as is connected, for example. And then what those functions are doing is essentially breadth first search. Okay, we can move on. Now, components in case of directed network. So a very good example is the World Wide Web network, where the nodes are web pages, and two nodes are connected if a web page references another web page. And for directed case, you know that even the shortest path thing is it becomes maybe a bit more a bit more non-trivial problem. But with shortest path, it's not a big deal. So the algorithms which can detect the shortest path, they can relatively easily deal with directed or undirected cases. So that shouldn't be a big problem. Still, we need to change, the way we look at the graphs and the way we consider them in case the graphs are directed graphs. So regarding the components, we have, in this case, two definitions. One is the weakly connected components, and the other one is the strongly connected components. And the weakly connected components says that two nodes are in the same component if they are connected by one or more paths. Okay, and whatever direction. Okay, so that's cool. Now, strongly connected components, that's a very heavy kind of definition, so very strict definition. It says that nodes I and J are in the same component if and only if there exists both a directed paths from I to J and a directed path from J to I. So you see it's really strict. It's really a strict definition. It's really a strict requirement to have a component be strongly connected. So it's easy. I think it's relatively easy to see that strongly connected graphs are always cyclic. So it means that they contain a cycle, of course, because we have um, a path from I to J, and then we also have a directed path from J to I. So either the cycle starts from I, goes to J, and then on the way back comes from J back to I, or maybe there could be even this kind of, so this is I and this is J, and there could be a path which goes like this, okay, and then on the way, so this should be directed, and then on the way back it comes like this, okay, and then the cycle, actually now this has two cycles, because now the first one could be this one, okay, directed, and the other one could be this one, of course, okay, again directed. So but at least we have one cycle, so it's strongly connected graphs are always cyclic, and we can always turn it to the other side. So acyclic directed graphs, so DAGs, have no strongly connected components with more than one vertex, okay? So of course a DAG can be a self, so if this one should be put into brackets, because we agreed that we don't really consider nodes with self loop. But anyway, the fully correct sentence goes with the phrase in the brackets as well. Okay, now let's consider random walks now. Okay, so what do they mean, or what are they? So a random walk is it consists of repeated steps, and on the graph, okay, so we usually start from a node, whatever, and at each end, so if we are standing at a node, then depending on how many edges it has, so now let's consider now the undirected case, okay? So if we have a node like this one here, and then it has so if it has one edge, then there is no choice, so we move on the next edge, so that one edge. So assume that we have two edges, then what we do is we choose between the two edge, we choose randomly, I mean uniformly at random. So the probability that we go to this direction is 1/2, and the probability that we go on this other edge from this node is 1/2. So for example, in this case, we toss a coin, and then we decide accordingly. Now, obviously, if it has, let's say, the degree of this node is, okay, we said it should be k. So if the degree is k sub I, then the probability that we choose an edge among the edges, one edge is 1/k sub I. Okay, so that is the choosing uniformly at random. Now we can actually analyze this kind of thing. Okay, so one more thing. How we do this random walk is that we assume that there is a clock which is ticking, okay? And then at every tick, we basically choose choose from the edges which edge we should move on. Okay. Now, one more thing is that if we have, for example, this kind of thing, okay, and then let's say that there are other edges from, so we start from this node, and then we assume that we move on from here. Okay, let me switch to red. So we move from here to here. Then again, now on this node, this very node, we have three choices. Okay, so because it has three edges. And then, of course, it can happen with a probability of 1/3 that we move back to the node from which we started. So that's also possible, of course. So that is a random walk on graphs. Now, if we take this from the mathematical point of view, then let's assume that PIT is the probability that we are standing at node I at time t. Okay, and so now let's see how we can calculate this probability. And this probability can be calculated in such a way that we sum. So what we do is that we take, so this is going to be I goes from 1 to n. Okay, and so you can see that what we are doing is that we are considering here the adjacency matrix, the entry of the adjacency matrix, and then, so if we had the adjacency matrix like this, okay, and so now the row I is fixed, we consider row I, and then j is the running index. So basically, what we do is that these numbers here could be either 0 or 1. Okay, so let's assume that we have and so on. So let's assume that we have 0, 1, 0, 0. Okay, and then it continues. Now, if we start the j running, then first we have a 0, and so this one here it's a multiplication factor, so it's 0, so it doesn't count. You can see that this 0 also doesn't count, this 0 also doesn't count. What counts is if we have 1. Okay, so in that case we have 1 over, so then it's 1 over k sub j. Now k sub j is the degree of node j. Okay, and so the degree of node j. So what is that? Well, that's that should be, so this j, so this node j, we know because in the adjacency matrix we have an entry 1 at j, and now j equals to 2, for example. So we know that because there is a 1 in the adjacency matrix, so we know that node I is definitely connected to node j. Okay, and node j, it can have, of course, as many edges as it wants, so that's for sure. And then, for example, if it has four edges, like in this example, then from j to be moving here to I, we have the probability that we have the probability of 1 over the degree, which is 1 over 4. Okay, so that's, so this is why it's it's, so then the degree, so now in this case is 1 over 4. Okay, because 4 is the degree of k. I tend to write d because that's more natural, but apparently in this book which we are taking is denoted with k. Okay, so K sub j is the degree of node j, and then it's 4. So now the multiplication factor, the whole multiplication factor is 1 over 4, and then we need to multiply this with the probability that we were at node j at the time, so one time step before, so t minus 1. So that's the thing. And now we can rewrite the whole this formula. Okay, now this should be actually boldface, as this is a vector. So we are just rewriting the formula now in such a way that D is basically it's a matrix. So A is the adjacency matrix. D is a matrix which is a diagonal matrix, and it contains in the main diagonal it contains the degrees of each and every node, and we take the inverse of that matrix. So this matrix looks like that we have k1 as a first entry, and 1 over k2 as a second entry, and so on, and 1 over kn, and then 0 everywhere else. Okay, and then if we multiply, so this is the inverse. And if we multiply with this D inverse, the adjacency matrix, then it has the same effect as here, written up here, as a division. Okay, so now if we go to infinity, then basically the whole equation turns out to be this one. Okay, and now we can rearrange it in such a way that now we have, let's say, so we basically we subtract, we take this part to the other side. Okay, so then it's p minus a d, and then yeah, so that's that equal to 0. And now we can take out vector p. So it's the identity matrix minus a d inverse times p equal to 0. And then, so this is written here. Then we can even rearrange it even more, taking out the d inverse from inside, from the brackets. Okay, and now we can denote this matrix d minus a as L. Okay, now L is just a notion right now, but now you can also see that actually this one, so now this is a matrix. Okay, and now this one, that one is a matrix times a vector. Okay, so that is matrix times vector, which is actually a vector. Okay, so now we can even rename it maybe as q, vector q, and hence we can write this equation in such a way that L times q vector equals to 0 vector. Okay, and you can also see that this is a particular equation, well, a homogeneous equation, but it can also mean that that this is an eigenvalue, sorry, an eigenvector problem. This is an eigenvector equation in which we have the eigenvalue, which we could maybe, so you know the, well, where should I write? Maybe here. So it's L times Q equal to kappa times Q. Okay, so that should be the general eigenvalue, eigenvector problem. And if kappa is equal to 0, then we get L times Q equal to the 0 vector, right? And this is here and also down here. So this is why it's written that that this d inverse times p is the eigenvector of L, and its corresponding eigenvalue, kappa, is 0. Okay, so it can be also shown, we don't prove it, that if we have a network which is connected, then the equation, the corresponding, so the equation gives this one as a solution, which means that basically P, so the probability vector looks like this. So that one is, so this both face one is the vector which contains only ones. Okay, and so this goes down to the fact that that P sub I is equal to a constant times the degree of the node. So the consequence or the conclusion is that the probability that we visit a node I is proportional to its degree. Okay, now this is just a normalization, so yeah, you can have a look on it if you wanted to. The conclusion is a nice one, that higher degree nodes are more likely to be visited or found. Okay, so that's the conclusion, and then we have seen even the derivation of it. Okay, so with this one, I think we can end the today's lecture. So this is enough for this week. Next week we continue with a large topic, which is measures and metrics. Okay, thank you very much for your attention. I see you next week.